So here we have a situation where there is a person of mass 80 kilograms standing on the surface of Earth. What is the gravitational force of attraction between them? Well, force of gravity is G big M little m over R squared. Now we were given previously that big G is 6.67565. And I'm going to write this number in a strange way, but you'll see why by the time we're done. Times 10 to the minus 11th. I'm just using a little bit different notation, but it makes it clearer the numbers we're looking at. The next thing that we would have is the mass of the Earth. And the mass of the Earth, according to NASA, which I've included down here down below, is 5.9724 times 10 to the 24th kilograms. And the mass of the person is 80, so that'll be 8.00 times 10. Now the distance between their centers is the radius of the Earth. Now you learned in Earth science that the radius of the Earth at the equator and the poles are two different numbers. And we'll start out using the radius of the Earth. Now in this case, R does happen to mean the radius of the Earth, but that's only because we are just standing on it at the equator. So we have a radius of 6,378.137 kilometers, but we need our measurements in meters. So kilo means 1,000, so we are going to multiply it by 1,000. So we get 6,378,137 kilometers, or meters, excuse me, or 6.38378,137 times 10 to the 6th meters. Oh, not so bad. So we have 6.378137 times 10 to the 6th, that entire thing squared. Now, why did we do it this way? The reason we did it this way is that the one place where people make the greatest number of mistakes in their calculations in physics is usually in this formula or its equivalent in electricity. And that's because of all of the numbers and the scientific notation and order of operations. So I'm going to show you an easy way to make sure you do not make those kinds of mistakes. So we kept the numbers, the significands, separate from the powers of 10. And so that we can now write 6.67 565. We'll put all the numbers together. 5.9724 and 8.00. We put all those together, and then the powers of 10 together. 10 to the minus 11th, 10 to the 24th, and 10. And on the bottom, we have 6.378137 squared, and 10 to the 6th squared is 10 to the 12th. So now you may start to see a little bit of the method in my madness. We can cross out these powers of 10 so we never have to type them into a calculator. 10 to the 12th renders this 10 to the 12th. This 10 and this 10 to the 12th becomes 10 to the 13th, and 10 to the 13th and 10 to the minus 11th is 10 to the 2nd. So we have 10 to the 2nd on the top, and now it's a simple matter just to do the mathematics of dividing those out. Multiplying and dividing those out. And what we get, it turns out, is 7.84052 times 10 to the 2nd newtons, which is 784 newtons. Now my numbers, this had 3 significant digits, 5, 6, 7. I can only report 3 significant digits because I'm limited by that 80 kilogram person with 3 significant digits. Now, if we went through the same process for the poles, we get 789 newtons. So in fact, if you sent someone to the equator at sea level and you went to the North Pole at sea level, you could measure a difference in their weight, 784 versus 789 newtons. And so why should that be? Let's just take a look at that closely. We know the Earth isn't, let me exaggerate it. So there is a circle, and we have an oblate spheroid, which is fatter at the equator and shorter at the poles. And so what we see when we're at the poles is that that distance, r, distance between the centers of the two objects, is less. Since they're closer together, the force is larger, so the poles we weigh more. And when we're at the equator, we're farther away, so the force of gravity is less, we weigh less. So that's how we could do that with the Earth and the weight of a person on the Earth. And now what I would like you to do is do an experiment doing the same calculations, both at the equator and the poles, for the gravitational field strength at the surface of the Earth. So you should pause your video at this point and do those calculations yourself. So we'll start with G is big G, big M over R squared. And that is 6.67565 times 10 to the minus 11th, which I'm going to do in parenthesis. 10 to the minus 11th, 5.9724 times 10 to the 24th. Notice we're missing that person's weight. And we have a distance of distance between the centers of 6.378137 squared times 10 to the 12th. So in this case, we cancel this 10 to the 12th, and we're left with 12th here. And 12th, 10 to the 12th and 10 to the minus 11th is 10 to the 1. And so we've got 10 to the 1. And the number we get in this case is 0.9800647 times 10 to the 1 gives us 9.800647 newtons per kilogram. And we, of course, in this case, we can report 5 significant digits. So that is 9.8006 meters per second squared, or newtons per kilogram. 9.80. And if we do the same numbers for the pole, we get 9.86669, which reduces to 5 significant digits of 9.8667 meters per second squared. So we see that the acceleration caused by gravity is greater at the poles than the equator. And that number is very close to our number that we use, 9.8, 9.81, 9.80665. Now, if we take that 9.80665, which I quote, that's an average for all the places on the Earth. And you'll notice it happens to fall between those two numbers, 880006, and so on. So we can see that this number lies between those two, which it should. The least it would be at the equator, and the most it would be at the poles, with probably the most locations being closer to, the value being between those two numbers overall. So that's how we would do a sample calculation of force of gravity and the gravitational field strength.